Being you guys are on a tight schedule, I'll go ahead and get started. Good morning, everyone. My name is Roger Fritz. I'm the head of AC-DC-HOTLINE and also the Nikola Tesla Group. And I've been in the motor industry for about 40 some years. And what we're going to talk about today is basically clean power and what it does to motors, and also introduction into the Smart D technology, which is a more of a pure sine wave output and a pure sine wave input type device for variable frequency. You're welcome to join today the Nikola Tesla group. I put it in the chat. If you have questions as we go forward here, you're more than welcome to, ask those questions, put them there, and we will address them shortly. I always introduce just briefly with, this little video about Tesla.
When you think of electricity, you think of Edison. But there is one electrical genius who is nearly forgotten. A man who dreamed of giving the world an unlimited supply of energy. His name was Nikola Tesla. This is the story of a modern Prometheus who changed the world with electricity. It was Nikola Tesla who captured the power of Niagara Falls with his alternating current system and made it possible to transmit electricity to all of America and the world. Suddenly knew he could recreate this rotating field by powering the coils of a motor in different steps or phases, like the pistons of an engine. The resulting forces of magnetic attraction and repulsion would literally twist the rotor in a circle, the electrical equivalent of the wheel. And all this was accomplished with alternating currents.
And the reason I bring this up is because, as you saw in the video there, that there was a pure sine wave that was fed to these original induction motor designs that he had. It wasn't for square waves. The IGBT transistor puts a lot of pulse out. And so I'm going to go ahead and move on forward. We have several videos available of difference in noise level, heating. Actually, the inventor of the VFD was actually a person clear back in the 60s with the NASA program that created this original thought pattern, but the technology of the type of switches, which are the IGBTs that are out there that control and rebuild waveforms, wasn't wasn't perfected. So over time, as it went to the SCR, then the GTR, and then now 90% of the drives in the marketplace are PWM IGBT drives. So what it typically does is it takes and converts the AC to DC here with that's a diode front end. Then it has a DC bus circuit, and then there's these big electrolytic capacitors in here that basically create us about 650 to 700 volts DC inside the drive unit. Then from that, they use the inverter sections, which are basically IGBT transistors, to fire these PWMs out to the motor, and then it controls the motor speed. When the cables are relatively short here, and you've got grounding rings in the motor, you've got spike resistant wire in the motor, they work relatively well, and that's again 90 to 95% of the the VFDs in the marketplace are built that way. So again, you see here where it rectifies it, creates this bumpy waveform, and then they have to take capacitors to smooth it out, and then they basically control the PWM here from 60 cycle. They'll spread it out to 50 cycle or all the 30 cycle, and you can go basically from 0 to 60, and then you can actually even go up in frequency, with a variable frequency drive. So it does create these these pulses in the input, and that's what they're calling harmonics. And basically, what it is it's you have a 60 cycle power, but when you have these pulses happening as it draws nonlinearly into the DC buses compared to load, um, you get ripples, and these ripples can change back and forth, and that's where the harmonics are showing up on the input side that are going to the the power source. Then you have the PWM that's coming out of the drive that is sped up and slowed down, and that changes both of these issues. But when you get harmonics, um, into the uh, load, this is a little video here I'll show you.
Sine waves generated by pulse width modulation. This PWM signal has multiple drawbacks. PWM creates currents that are destructive to the bearings and insulation, resulting in the premature aging of the motor.
So that's where I want to talk about what's been done for quite some time, about harmonics and the understanding of the mitigation that's out there, meaning the, ways to get rid of it. So there is a compliance requirement, and I know a lot of power companies are becoming more and more involved in this on clean power VFDs. And you're supposed to be IEEE 519 compliant, but they've kind of overlooked it because also the units that they're putting out from solar are inverters, basically creating sine waves to put back on the grid. So they're masking the problem. There's actually in Southern California a massive generator system. It's a motor generator system where they draw on the load, and what that does is that inductive load of that giant motors down there, and then they're running it back to generators, clean up the waveform that are being created, by some of the power quality issues that are out there with solar and wind because they're not producing the same linear. They're producing nonlinear power, not producing pure sine wave like the old generators did. So from that, you get issues, and there's different things that have been done for quite some time. Like these are, deep well submersible oil pumps, and they're actually massively requiring what they call these VFD pure sine wave filters. So they put this on the output side of the drive, and it does clean it up, but there still is a lot, quite a bit of DVD down here in JAGs in it that is not able to be overcome. And then on the primary side, what they're doing is because of long lead lengths, they're putting in specialized shielded cable because that choppy input power is distorting the power source. So this gives you an idea of the PWM output signal. This is the harmonic side of the output. And then what happens is because all of these harmonics, you get imbalances. And so you get what they call common mode voltages fed to the motor. And that's where those spikes come from that you'll see. And that's why everything in the 80s and 90s, everybody went to special insulation in the motors. And then now they're coming out with, where they have actually, the special motors. So again, you get the harmonics fed back to the grid because you have a diode front end. Um, and so what they've been doing for quite a while also is they've been taking the variable frequency drive, which is the standard is a 6 pulse diode. And then you've got your bidirectional IGBTs, and then that gives you your PWM output. The issue is that these harmonics that are shown on the previous slide here, both on the load side and the input side, what happens is, and not being IEEE non-compliant, you'll get transformers and cable overheating, and then you'll also get all kinds of erratic problems that people aren't aware of that are happening in their PLCs, their process controllers, in plants. Um, and so it ends up, just creating more and more and more of an issue. We've done a lot of work for even PepsiCo, and with this 40% total harmonic distortion that is coming out of drives, by the time you got multiple drives in there, like 30 or 40 of them, the whole building becomes more and more, higher noise, and it's not IEEE 519 compliant. Um, So then they've come forward and they've actually started requiring more line reactors and then these harmonic filters on the output. So you put, the line reactor on the front that helps mitigate some of this um, uh, harmonic content. And then you've got the output, which is basically also trying to mitigate some of the content. These are all non-active. So again, what's happening is that all that frequency that's out there, power doesn't go away. It goes somewhere. And most of the time, what they're trying to do is isolate it off the ground and feed it into the network. So then they've moved the VFD where they actually put in more diodes. They got 12 pulse, meaning 12 sets of diodes, 18 pulses, and 24 pulses. And what that does is it mitigates some of it, but you have to have a transformer that steps it to the 12 pulse and the 18 pulse. So you have multi-step transformers, and that becomes very expensive. Again, you still have the PWM out to the motor. Um, uh, let's see. Then they've created what they call an active front end device, which is another inverter that they have that they're feeding back on the grid to push back against those harmonics. And this was developed originally by the government because they needed to keep clean power, on the ships, aircraft, and that in the marketplace. So they're still using the IGBT up here, but they created all these masks to go back against and regenerative against those bad harmonics, and it one cancels the other. There's also been a matrix drive design which has been out there, which also then feeds back. The disadvantage of that is it does drop the input voltage down to about 85%. So it ends up sucking a lot of the power off, and the total efficiency isn't as high, on other architectures. So, and then it still has the impact that happens out there on the electric motors. So the motors still end up seeing that harmonic content. So you can see here the different options out here. This is a conventional, um, with like line reactors, and they, mitigate it. This is just a straight conventional VFD, and you can look at the choppiness and the current waveforms. And then there's also, we'll get into a little bit further here, the clean wave output type. Um, so you can see that the actual power factor on the line side, um, ends up staying up here at continuously above almost 99% on the Smart D, per wave, pure sine wave VFD. Um, Adversely compared to the conventional, here is it drops off dramatically, and then the ones with filters are down here, but you can see that it's still about 94% power factor. A lot of them play around with displacement power factor and real power factor, but at the end of the day, the power companies have become, very much aware of this, and you'll see that on your power bill, that the total kVA demand of the buildings is going up and up. Um, this is an idea of where the line distortions are happening, in the marketplace. You'll see that the conventional VFD, noise is up here anywhere as high as 40, to 35%. Um, and the actual IEEE 519 is supposed to be less than 5%. Um, so you'll see with the active front end type, here with the all the filters, they are dropping it down here, very close to what we're doing on the input also, that, at the load of the motor that we're setting here, at roughly about 5% total distortion. Um, and then on the voltage side, we're setting here. This is a very very strong source out there, and you'll see that the conventional, can ramp up here to about 3.5% voltage. But the power companies on the IEEE, they want this 519 less than at or near 5%. And so that's what they're doing to get it there. And this is an idea if you look at on a scope fluke meter. That shows the standard VFD, you see all of these harmonics going all the way out, clear to the 50th order, meaning like 5,000 hertz, you know, noise. So what we're really doing is creating a radio. And you can actually hear the switching in the motors. You can hear it on the power lines. If you've got an AM radio, it radiates off. So all this additional um, multi-harmonic currents also draw additional power. Um, but as you can see here, that here's the order of the one with the Smart D, um, you know, which the difference is that our switching frequencies are about 210 kilohertz. Most VFDs are running at 2.5 to 5, sometimes 7. So having that high frequency switching, plus our EMI filters that are built into the VFDs, we're able to clean this up, all the way through the spectrum. From that, the PWM has the impact on the motors, that it basically starts creating additional heat because all these jags here, the motor acts like creates counter EMF and pushes back against this, but it doesn't exactly match that because it creates it based on a pure sine wave of the rotating speed of the motor. So these two start conflicting each other, and that creates additional heat that happens up inside the motor itself. Um, Also, this shows you the spike rising of the standard VFD with the IGBT, to where you've got your pure sine wave input over here before the diode front end, except for the harmonics. Plus, you've got these spikes that can happen as it first fires. So it triples to several, switching characteristics of the component, and then basically on the physical load of the motor itself. So from that, they've, on the typical IGBT drive, you put in these large sine wave filters on the output to get rid of that, and then um, still get some of the choppiness I showed you earlier, and you've got to have, specialized cable to create and get rid of the corona discharges that happen on the cable over long leads. So that's why if you look at all the specs on drives, they're all saying if you have really anything over 50 feet from the motor, you have to be very careful, about both windings and cable damage over time. So the issues over here are, motors, they got to be inverter duty. They got to have typically grounding rings in. You put in specialized VFDs, you put in line reactors on the input, and you put, sine wave filters on the output to clean all this up. Where if you use the actual Smart D control, the outputs, you don't need specialized VFD cable anymore. So what they're talking about here is this common mode voltage, which is causing the bearing issues, so that extra PWM and all this choppiness, goes into the motor here, and it goes into the stator winding. But that extra, basically because the voltages are not common from one to the other, so they don't cancel each other out, you get a capacitance effect between it and the frame and it and the rotor. And so it creates what they call circulating currents that want to go through. And where they want to go through is they want to go through the bearing, because that's the quickest form to get back. So you'll see, there's multiple companies out there, from carbon brush companies. There's, Argidis grounding rings that are out there that are needed to basically try to eliminate this common low voltage. The problem is you got to read the fine print that they're saying that those brushes and rubbing points of the brushes have to be cleaned every year, or what'll happen is it'll start building a film on them, and then it'll stop that, and then it'll still take your bearings out. So then they went to, ceramic balls in the bearing that helped it. But all of these things, in my opinion, are just band-aids. They're putting band-aids on the real problem is the VFD frequency of the IGBT. So let's shoot about the grounding. And this is an idea what that happens over time. This happens to be the inside of a bearing, and it starts creating pitting, frosting, and fluting. So over a period of time, there's been several guys that we've ran into where they have long lead lengths, and in mines and stuff, they can't have this. So they end up going in and changing the bearings out all the time. And they're trying everything possible to eliminate those bearing failures. And a lot of people didn't know it until after about 3, 4, 5 years, and all of a sudden the motor started failing prematurely. There's a fellow in France that I've met that actually has done a study of 900 motor applications with and without VFDs, and has found that the failure rate of the drives with VFDs on them is roughly 40% higher than it is with just going straight across the line. So you got to look at, well, what is the true advantage of the putting the frequency on? Yeah, we save a lot of power because we're reducing the loads, to the item. So again, you've got the sine wave filters required, the inverter duty motors, special cable, and then there's these common mode chokes that a lot of guys are putting on, again, to try to accommodate that issue. We've used some of those on bigger drive applications, where there isn't available, the MOSFET yet, which makes the difference in the other drive. And then they've used insulated bearings and then the shaft grounding rings. So, if we have a drive that is calmer and cooler, because we're providing pure sine waves, we don't get all of those disadvantages. We don't need the grounding ring. We don't need the special insulation in the wire. We can use standard. I mean, we put it on motors that are like 30 years old, and have had zero problems with them.
Over the past 40 years, technology has evolved at breakneck speeds. Over the same time, drives haven't changed, still delivering the same pulse squared signal, damaging motors and polluting the grid with harmonics. What if a drive could generate a clean sine wave? Introducing the Smart Drive from SmartD, the first ever compact, clean power drive. The Smart Drive delivers a clean signal for lower line losses, higher motor efficiency, and prolonged motor life. Gridside, its active front end ensures ultra-low harmonics and full regenerative capabilities. The smart drive system occupies less than half the space of traditional drive design. Because the filtering is built in, there is no need for external filters or reactors, unlocking high-density applications like never before. A drive has never been so easy to install. 3 wires to power, 3 wires to motor, and that's it. The intuitive touchscreen user interface confirms when you are ready to go. Configuring is simple using the SmartD mobile app, which also monitors your drives and sends you alerts. The Smart Drive excels driving HVAC equipment and water pumping processes. It keeps fans and pumps cooler and operating more efficiently, even when low harmonics, high temperature, or long cables are required. The new standard in drives is easy to install and configure, takes less space, is more efficient, and extends motor life. It is simpler, smaller, smarter motor control.
So this is also a test that we're done to show the differences between the standard VFD with the PWM going to the motor, and then you'll hear the decibel difference of the pure waveform. So the motors literally run extremely quiet. That was at zero, low load, and this is at 25% load. You'll see the differences in the noise. And these were all done by independent test labs. So, at the end of the day, we have very low harmonics, no common load voltages, and this is all from external, lab tests that were done. We have no problem with long leads. We don't require anything between us and the transformers. Another advantage that they have is that we don't use electrolytic capacitors. So in a standard VFD, you have electrolytic capacitors, and if you read the fine print, it says that within 10 years, you're supposed to be changing these capacitors because this film ends up drying out. We actually use more of like an oil-filled type capacitor because we don't have all of those high harmonic ripples that we've got to clean up. So a lot of drives that I hear from like customers we have out in Arizona where the drives are 6 or 7 years old, and all of a sudden, they're calling and needing to change the capacitors because of the high heat that's drying out the film inside in the capacitors. But the IGBT can't get away from it because they have to have such high microfarads to clean that up. So again, this is more of a detailed comparison of the output of the Smart D. Literally no common load speaking voltages. And we don't have all of these ripples, both in the input and output of the drive. And then this is a comparison to if you go and you put a passive harmonic filter on and a sine wave filter output on a standard 6 pulse drive. And it is better, but we still have the same issue about this common low voltage. So what ends up happening is you still have to put the grounding rings on, and you need to put long cable length, filters on. So this is the peak load common mode voltage current comparison. This is also on like a 500-foot, cable issue of the actual peaking voltages, that happen on a conventional VFD. If you do put a filter on and that's at 4 kHz on a VFD. You get your conventional, and then you got the clean power VFD. But you see also here is we don't have that voltage drop that you lose, which is additional energy lost from putting a output filter on. So every time you put a filter on, you lose a percentage of your power in both the input output filters that are out there because that energy has to be used. This is a comparison of the temperature of the motor itself. Um, you'll see here, at the various loads, what the temperature load is, and you can see comparison to a VFD on the same motor and loads. You'll see that there's an 11% increase, 9% increase. That's why most motors with VFDs, they don't recommend you running into the motors, into service factor, which we have no problem with the service factor. You still get to use it. And what the real difference of the technology is what they call this silicon MOSFET controller. And it really came about because of the auto industry. They've moved on forward, started creating these MOSFET devices instead of the IGBT unit, and these keep evolving further and further ahead. So we've negotiated with them, but you can't just stick the MOSFET into the standard VFD drive because you have to have special algorithms, a lot of research that's gone into this, which they've done, almost 8 to 10 years of working around this and working alongside the MOSFET um, transistor devices out there. And these all run, at about 2000 or I'm sorry, 210 hertz, kilohertz. And the IGBT, they typically are firing anywhere from, the pulses are running anywhere from maybe 1.5 kilohertz to 5 to, I've seen 10. On some small drives are running them up a little higher than that, but you still get the effect of the breakdown. And you can see that this is where they've been moving so far. They've been heavily involved in robotics, uh, smaller applications, cars. They're working on some of it, wind, and very customized application. But it's moving on in, to take over the VFD market over time. So the high density, 3 level rectifier with a active front end on it. We also don't need any dynamic braking. So we actually, any energy created back in the VFD from loading. So let's say you have a pump jack, you have a escalator, elevator. Well, when that motor becomes basically feeding power back, it's got to be given, taken somewhere. You can't have that excess power. So they have typically on a standard VFD been dumping it off to actually resistors. So you'll hear a lot of these, resistor banks that are added to VFDs, in cyclical applications to eliminate basically voltage spikes. And we've also created multi-layer outputs on this. So we're not just one switching device, we're multiple, so we can stage it. So we can actually then, at high speeds, we can create that power waveform, with high frequencies, 105 to 210, kilohertz, where everybody else is between 1.5 and roughly 10 kilohertz. So that's where all those jags are coming from. And then because it's in the high frequency range, we're using a lot better LC filters to reduce any noise that is created. So our output becomes very clean on the output side. Plus we have the active front end on the front side. So you can see we literally have very, 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 very minimal any noise compared to all of this noise that's created. And the only way you can see that is with a Duranitz meter, a Flukes meter, and most of the time these are, in the price range of $6,000 to $7,000 to ever see it. A standard amp meter only is based around your 60 hertz firing part here, not at these, so they don't ever see, those currents that are going out to the motor. But that all that energy's got to go somewhere. Let's see. So, this is the electronics are going out there. And, we have no problem going long lead lengths, um, to eliminate all of so you can see our comparison between the standard out there with those filters. This is the output with the DVD filter, and this is an output with this. So we have no problem. There's no peaky voltages, no EMI to go out there. So the motor likes this. There's no fight going on between the motor and the drive. Um, so to kind of sum this up, you look at the impact of the differences, and by the time you add the sine wave filter, the special leads, the cables that are all out there, active front end in many cases to try to be that, all these line chokes, insulated bearings, you get a massive cost and also additional power loss in the total system. Where when you use the Smart D technology, the motors run 9 to 12% cooler. You need no special cable, you need no special foil in it, and you can use standard bearings, in the motor. And we've had applications where we ran up to 1,500 feet where they were not able to get the problem solved. And we came in and actually put the units in, and it cleaned it all up, and they're able to go forward. So motors stay happier. I've already went through the voltage side there. And then this is the for the grid side, we do meet the IEEE 519 specs, which is required so that the current waveforms, don't cause this distortion out here. So it becomes, very clean. This is a comparison, with the standard with a 612 with an active front end. Yeah, they can get there, but you have a very expensive active front end, or the matrix. But the additional on the matrix designs is that you lose roughly about 15% of your voltage. So the total efficiency starts, hammering away where we're pure sinusoidal, standard motor, standard cable. And we didn't need no output filters, and no loss of additional efficiency. So, I mean, if you start looking at these extra percentages of losses of 2%, 2%, 2%, outside that 2% on a 100 horsepower motor is a lot of power. It's like 200 watts of power you're just throwing away all day long. The drives are built, very simply, have, a lot of IO input. They have, the HMI built in, it's detachable. So you can mount it remotely if you need. The terminal blocks, the power terminals are here just in and out. Does have a replaceable battery, for the real-time clock and inside. It's got USB ports, so you can, talk to it, directly through a USB cable and the firmware. It's also got a, unused J45 there. And then it's got an HMI port, so you can remote mount it. And then it's also got a full Ethernet port to go to a gateway. A little bit about the front end of it. It's a touchscreen based front end. So as updates or changes happen, you're able to download that in, very easily. And this is the configuration of the I/O that are in there. It's got the Modbus TCP here, and it's very user-friendly through networks. It's got so you can, from your iPhone, there's an app that you can basically program the driver. If you have set up programs, you can download them and dump them in, very quickly into the system. The startup wizard, very, very user-friendly. So you can, download, upgrade, set your frequency. It's got PID loads. Currently, these are the power ranges that have been released that are under UL. They are going up to 150 horsepower here in 2026. And we also have both 600, 480, volt power sources. The other issue that's out there is there's a lot of energy programs out there. So the biggest factor on VFDs is, how do you get it installed? How do you get it paid for? How are you going to get, the capital money to do it? So in the United States only at this point, we do have a zero CapEx program through AC-DC, which is our company, for smart motor controls. There's a webinar coming up next week on the 20th, at 2 p.m., which is basically how to access and what requirements are on to actually get into that energy program. We also take and unlock all the utility and government rebates. This is through AC/DC, and get that detail, to you, to basically help offset, the cost of the controllers and installation. So this program actually ends up being zero cost. We use, excuse me, we use programs that are out there to where we use full ASHRAE auditors. So we look at all your applications, look at all the details of each motor, get that into our database. Then we know what the power differentials will be. And then we do a shared savings program over 5 years that ultimately pays the equipment back. And that's it, that's out there. And then there's many additional, rebate programs where they'll pay, like on a 50 horsepower motor, sometimes in the in Boston area, under both Eversource and with National Grid, that they pay like $5,000 in incentive. But we help you access that. We make sure that also all the detail, gets presented to the power companies so that you get your rebates, and get that pre-qualified in advance. And that's very important. If you don't get it pre-qualified, if you buy the equipment and then try to go afterward later, they don't like that. They want to do it afterwards. So I appreciate your time today, and I'm